Hello, everyone, and welcome to Learning Rust with Git Oxide. Today with our host, Sebastian. Hello, hello.
Hello. Thanks for having me.
Yeah, a pleasure, a pleasure. I will switch right over to you because you are supposed to lead us through some more Iterator stuff, right?
That's true. Thanks for handing me the word. I hope I get something together quickly based on what we ended up with last time, which was iteration over an array with a bunch of own strings or heap allocated strings, these guys. We didn't actually ever talk about the difference between str and string, so let's note that down for another time. In the meantime, we just take this as something that is very much owned and not copy, so we can try ownership a bit more if it comes to it. All right. Last time we figured out one specialty by ref, which allows you to do cool things like add things to a base iterator temporarily, which can be useful for parser related things. If you have an iterator over tokens, then yeah, you can consume these tokens and kind of make sense about them like this. So there's more cool stuff you can do, and one of these is like, what happens if you would like to transform the content of an iterator, but the transformation could possibly fail. And how do you handle errors? There's multiple ways of doing this, of course, so we try to get through a few of them. So maybe we start out with making this a binary string here. Like that. And now we would like to convert this into an actual string. And that should be possible because this encoding here is kind of by nature the right encoding. I mean, that's just ASCII encoding here, and UTF-8 to be specific, but it just uses the ASCII subset. And we know that because that's just how Rust implements its string literals. So it's kind of something you can bank on, at least if you see it in your Rust code file. So all these transformations here, they should work, but we don't know that. At least there is a possibility for failure when it comes to the type system, because the value doesn't matter in the type system, at least not here, because that's a runtime context, right? This is not statically known to Rust, even though it technically is. But what I'm saying is that if we would like to write an iterator that transforms these into strings, we can do so by using a quick map like this. And a map takes the value, and we should be able to pass it here from UTF-8 lossy. No, let's just give it a vector then. Like that. Okay, this into, it doesn't like that, so I try to convert these strings here into, or these byte strings into a vector, so that I have something that I can try to decode as UTF-8. This is what from UTF-8 does. It wants to own the data because it will just make it the underlying vector that is the string, because strings under the hood, they're just a bunch of bytes that are owned, but we know they're UTF-8. So this is why this wants to have a vector, because it just checks it and says, okay, this is now me. But of course, that check could go wrong. And this is now what we have in our iteration. So first of all, why does this not work? Why is into not happy? Because we can't convert from, oh, look at that. What's this?
So yeah, this is an array, right, of length 1, or basically a referenced array of U8s of length 1.
Yeah.
And I cannot convert this specific type into a vector of U8s.
Yeah.
Which seems weird because that should be doable, right?
Yeah, should be doable. I think it might be a reminder of Rust not dealing so well with arrays because you had to by hand implement every conversion from every kind of array, because that could not be generic, that amount of bytes in the array. But now it can be generic, but it's still not implemented. So I don't know when that will happen. Maybe it's on roadmap, because it's kind of a bit surprising, right? This also means, because arrays have to be homogeneous. I don't know if I pronounce that correctly, actually. So if homogeneous. That sounds better.
Maybe.
I take it. This now doesn't seem to compute anymore. Okay, it only dislikes the first one, the second doesn't matter anymore. Because we also see that this is now an array of 2 items, of 2 bytes. And that's also not what it wants. Which is interesting, because this literal syntax here, it basically just creates an array of bytes for you. It's a syntactic sugar for this. So in order to store variable length byte slices, we have to convert these arrays into a slice. This is how we can store it in the same array. And yeah, there should be multiple ways of doing this. One is to index it and say, okay, here, this is just a short form for this, 0 to the end, exclusive. And this creates a slice. And now it's happy already. Why is that? Yeah, definitely is happy. Because
so the first element gives the type, the rest can be inferred, and then it's happy.
Yeah, that's the thing. This is not about type inference technically, I think. It's more about, I mean, probably it's related somehow, but these are technically still, they're supposed to be byte arrays. And Rust does not automatically convert things. So I have like it wouldn't call into automatically here to convert an array into a slice or something like that. Which, does that work even? It doesn't even work. Okay, it's not implemented, this into. So I don't know what happens here or why that works. Maybe it's some special thing just to make this a bit more convenient, that it automatically transforms this, or maybe it automatically dereferences it. Let's find out which conversion is happening here. So is this also creating a byte slice? Oh, look at that. So auto dereferencing is happening in this context. And that's, you exactly know it can't be many automations because there's only 2. Auto dereferencing and the dot syntax here. Like if you have a value and you can say dot, then if the value is borrowed, that will work too, because it kind of automatically dereferences it. So I think it's kind of auto derefing all along. So that's the same as this then. So probably we can just write this and call it a day. Oh, whoopsie. Okay, that's interesting, huh? So apparently this syntax here does not create a slice. It actually just creates a borrowed array. Okay. What about this? Like, does it have multiple deref steps or something like that? No, it can't. No. So that is interesting, isn't it? So I still don't really know why this derefing gets to the slice and the other one doesn't.
Probably again something like it just forces you to be explicit, and then after that it kind of knows what you want.
Yeah.
It's probably more clear like that as well.
Yeah. It can make these things up though. Like it shouldn't be able to. Like you should be able to do this manually, I think. But this, I really don't know. But anyway, now it compiles. You know, these things, I never thought about them. But in these sessions, I usually dig deeper than I ever did. All right, let's print this one. Let's see what we have. And conversion was successful in all 3 cases. That makes sense. So can we also make the conversion fail? Maybe put a 0 here. Okay, cool. So that computes. There's other ways too. What about this? Is this valid syntax? Okay, good. I found one. So that's not valid. Yeah, because that's the high bit of UTF-8, right? UTF-8 sets the high bit to say, okay, there's another piece of the puzzle coming in the next byte. And there must always be another bit set, I suppose, for this to ever be valid, because otherwise you don't encode anything. And this is why this should never be by itself. Okay, cool. So that fails. Nice. And now I'd say, well, we don't want to print the error here. We want to print a string. If I try that, it probably tells me that it can't do it because we still have a result. And now finally, after the recording froze.
Okay.
Yep. Oh, did it? Oh no, wait. Maybe it's just the screen that froze. There is definitely something wrong. It doesn't show the time. It doesn't respond. I can't go there with the mouse. Maybe it's just a display.
Safe, but still probably safer to restart just to make sure it doesn't go to waste.
Yeah, or we just continue because I think it never crashed or anything. It's more like might be a display issue. Second display might be frozen, which also never happened. So I don't know. Let's try one desperate thing. Let's restart this, and everything is fine. Ha! I tried to trick us. Wow! And now something else happened. Now the resolution of my main screen changed to something else, but it's okay.
If you can still see, it's good.
Yes, it's fantastic stuff, technology. It really does not work at all. Okay, let's make this work. So for this to work, now we would have to kind of unwrap this thing, right? We could just do this. But then the program should crash because we do have an error here. So we can't really do this. And now it gets interesting, error handling. So one thing we can do is, of course, just do this. Okay, we can't. Results. Does this work? Let's see. Do we have anyhow still? Doesn't look like it. No, anyhow. Can I do something cool with IntelliJ here to automatically edit? No, I cannot. Okay, that's fine. Then I quickly do that. No. That's something that usually happens. You don't have to do this. I mean, one way to do this, what would be a way that definitely works?
Oh, you just use the same error, I see. Okay, yeah.
You don't have to always convert it to some higher level error if you just have one. That should be fine. And now this does compile, but it still fails with the error here. Okay, so one way of doing this would be to skip everything with an error and just not looking at the errors maybe. Okay. Yeah, so it's like filtering for things that have errors. And then if there is no error, unwrap it or something. I don't know. So we could do this is okay. It's not particularly happy because...
don't you have to invert the order? Like first map and then filter?
In this case, no, I think. Or... Oh yeah, right. You are of course right. This is why it doesn't like it, because we don't have a string yet.
Yes.
But there we go. I would have loved to say that was a test, but it wasn't. Okay, so that works. Cool. We now get to the end of the program and get to print everything. So that's one way of doing it, but that it does look a bit clumsy, doesn't it? Like,
is that really what you do? You just ignore the errors essentially, just throw them away? Seems irresponsible.
You don't really throw them away either. I mean, this is the thing with this kind of syntax. That's we tried something and it kind of works, but it's not idiomatic, I'd say, because we still unwrap something or we still deal with errors even though we know there is no error. And that, of course, is kind of an ugliness that should be fixed. But it's a valid way of handling this by just saying we ignore errors. I mean, there's multiple ways. I don't judge. It just depends on your program's needs, I suppose. Okay, so
yes.
Yeah, filtering and mapping is something you always have together or often have together. So there is something cool that is called filter map. And we can just say, just take the OK value and put that into an option. So filter map calls a function that returns an optional. And if that optional is sum, then it's part of the iteration. And you can map it to some other value. So whatever is in there is the new value of the iteration, and if there's none, it skips the value. Hence filter map.
Cool. So it also unwraps the option then, so you actually get a string out?
This is what the OK does.
In this case.
And it's not unwrap. It just says, I mean, let's look at the code.
Yeah.
It's this. It's so nice to just look at the code because then you see what it really is. And of course you could write that yourself.
Okay, but yeah, you still return an option from OK. So filter map basically returns an option with the mapped value. And then in the for loop, it already kind of unpacks it. So you're not left with the option, but you're left with the actual value.
Yes, good point. Like this is like if filter map wouldn't actually be a filter, then the filtering is based on whether an option is sum or none. And this is what makes this so powerful. This allows you to effectively degenerate information. You have results, but you just ignore the error and just look at the OK value if it's there. Yeah, let's actually remove this warning here. And this still works. Nice. So we also have seen this is one way of doing it, but maybe you either want all to be OK or none to be OK. So we had this kind of mixed result where we did this. Let's do the map again. So this is the other way of doing it. We try as much as possible and abort on the first error. But we could also want an all or nothing situation. We don't want to process this unless it's completely valid or completely valid. And I think that's the last thing we want to look at. And in order to do this, like what do you have to do to make this work? like you have to check every single value before you can then pass all the good values on, right?
Yeah, I mean, is there another function for this? I know in TypeScript and JavaScript, they have one that does exactly that. It just checks the predicate for every single elements in the vector array. And then if all passed, then it basically returns true.
Okay, so let's do that then. This is a case for by ref, huh? Maybe. So here we have our conversion. Can we just assign this? I'll just call it iter. Okay. And then if iter by ref, I don't know why code intelligence is completely done here. Can't handle the I can't handle the iteration for some reason. Okay. By ref. So you say if you can say all. Right? So like that then is okay. So now we know that all values are good. And now we can do the same thing again. And we know this is never gonna happen. But we still have to unpack it, right? We still have to deal with it. And we don't even run into this branch because not all are good. And this is how you would do it in TypeScript and so on, right? Is what you meant?
I think so, yeah, exactly. That looks similar.
Yeah. So also what we do is this, huh? We have to iterate once, read only kind of, just to see what's going on, and then we iterate again, but still have to deal with errors technically because we still did not unpack the good values already. Which seems fine, but also, I mean, it's definitely fine because we just use the existing memory that we have. We don't just drop the good values into a new array where we kind of keep the good ones. And if all are good, then we kind of have doubled the amount of memory potentially because we kind of store everything again. Kind of. It's not really the same thing anyway, so it's okay, I suppose. So I think from a memory point of view, you can decide to write something like this just to maybe not allocate a new vector. So what am I talking about? Like if you have a vector here that is just for the good values, then we can in theory iterate through it, right? For a string in these. And now we have a result here. We could match on the result or something like that. And if you have a good value, note how I always just choose the same name instead of making up a new one. Shadowing, rebinding, all cool, all nice. Never causes a problem. Then we keep the good value, or otherwise we bail out. And then in the end, we can do that iteration again and print only the good values if there is good values. But now they're unpacked already. Okay, but we don't have all good values yet. Let's try that again. So that does indeed work. But it also is kind of cumbersome to write that. It's a lot.
Yes, you have two different loops essentially. Not very efficient or elegant.
Yeah, not very. Yeah, if you write that a lot, you will probably dislike it. This is also why there is another way. And that other way, yeah, let's stick with this. Let's do this. A vector of whatever you infer. And then we take this portion here. And now we want to collect into what's on the left-hand side, into a vector in this case. but with an intermediate step that is, please collect it into a result first. And it doesn't like that very much. Let's see what the problem is. What I wrote here that makes no sense. Expected struct vac wanted a, yeah. So on the left side here we have a vector, but on the right side I say, let's give me a result. Let's see if Rust is smart enough to understand that I want to get rid of this result and just keep the good stuff. So keep the OK value. This is the inferred value here. I could also write it like this. Same thing.
Okay, makes more sense.
But this gets filled in automatically now that it sees that. So look at the compiler. If you write a compiler, like how much kind of look ahead you have to do to understand this. Like what's okay? What's the okay value here? Let's see what else there is. What's on the left side? What's on the right side? Interesting. So that works. Okay. And all is well. And of course you could indeed just write this into one line if you want to. You can just put this here. Or if this is easier, you can put this here. I want a result of something. And then on the right-hand side, there's nothing to do anymore. Because the value can be inferred.
Yeah, I mean that kind of makes sense. You just put the type wherever. Yeah, you kind of mixed it before. You said you want to end up with a vector, but you're collecting it into a result. That was mixed up. This makes more sense. But essentially, this collect is then transforming the vector of results into a single result that has the vector with the values.
Yes, that's correct. So we could also write this just to spell it out. And maybe that is what you should write the very first time, just to make it more understandable what's actually supposed to happen here. So it's more like a transposition of all the values. It's exactly the loop we just had. And it's something special.
What happens with the errors then? I mean, this basically also says you're ignoring the errors, right? Because you're throwing away the individual errors and just saying, okay, something went wrong there, but I don't really care.
Actually, you do, because this is a from UTF-8 error. So the first one is going to be canceling this whole operation. So you don't collect all errors. And that might be another thing you might want to do, collect all errors and do something with them. And this is something, to my knowledge, that you can't do. But I might be wrong. So you see a value of type result vec string vec error can't be built from this particular iterator. So this doesn't mean it can't be done, because obviously you could, right? But it's nothing that collect can do. So this would be the other way of saying, yeah, I want to keep all the errors and then, you know, give me all of them and I deal with them. But that's something that you can't do with collect. There's a crate for that though. There's a crate that allows you to do all these kind of different ways of error handling, kind of with a bunch of methods that are extensions to existing iterators, similar to collect. Yeah. And this is something that it kind of warped my brain the first few times I used this, because it feels so magical. Like, how does collect know all of that? Why? And the answer is somebody programmed that in there. And this is why it works. You see, you can also simplify this and say, I want to collect into a vector of things. So that usually makes it easier. Say vector of things, just let it infer the type. And now you see we are back to square one where we have a bunch of results here that can't be displayed anymore. You have to debug print them because that's all that does. But what about deduplicating strings? Does that work too? Sure. So let's deal with errors and deduplicate things at the same time. Okay, so that probably doesn't deduplicate. Let's print this just to see what's going on here. Okay, let's have some duplication going on. Oh. Duplication present. Okay, how can I deduplicate with just that?
Is there a special type for this, or like a special data structure that you can use? Set?
A set?
Is that the one?
Yeah, that's a great idea. That should work. I should be able to collect into a set. Yeah, voila, deduplicated. But also reordered, I suppose. Like now it's kind of reverse order here. I think that's what we see. But fair enough, deduplication works that way. And that's exactly how you dedub things, by collecting them into a set. And you have to do that one way or another. You can collect it into a vector, and then you sort, and then you, yeah, better just collect it into a set. But deduplicating vector, I think that also works, but I don't recall ever having done that. Let's see if there is a way that I just don't recall. Let's remove this. Good. There's a dedup function, see? So on a sorted vector you can do that, otherwise it probably just does nonsense. So fair enough. And that probably has, you know, might actually be faster than a hash set depending on what kind of data you have, or use less memory at the very least. Yeah, depends.
So this collect function, so that works because it just knows how to convert certain things. Like it knows how to, for example, transpose result vector or vector result, and it knows how to convert a vector to a hash set and stuff like that. So all of these things are written somewhere, and collect just uses that.
Yes. Let's see if you can make sense of what collect does. Collect takes something that can be, or that implements from Iterator. So probably from Iterator is implemented for iterators at the very least. Let's see what this one does, because so far and from Iterator has into Iterator. So in a way, just an inverse way of writing. Convert that into an iterator, please. And I'm sure that has a very good reason to do it this way. Okay. And then you get, it's amazing, huh? I mean, I really don't know why that works at all. Like if this is from Iterator, but from Iterator is really just, implementing from either where T is into Iterator. Okay, but what is this implemented for then? Where's the implementation? Okay, we have a bunch of implementations here. For result, for example, I would expect, where is result? Where did I see it? Here. Okay. Iter process results, iter collect. Look how all this is yeah, nested and, you know, with smart generics. That's the kind of stuff you don't write so easily. But do we eventually see the code that looks a bit like? No. I mean, all this is just so, you know, decomposed into little pieces and parts, and if you combine the little pieces, they compose back together to what they were supposed to be, which just shows how cool the type system is, but also it's the kind of thing you just want to use but not write or look at. Let's go back. to collect, which looks a bit more approachable.
So it really is magic then.
Yeah, apparently. I would not be able to, I would have thought there's somewhere a loop that I wrote, you know, okay, then you do this, just do it. No, not like that. Okay, and now something broke because, oh yeah, we want into iterator here. I thought I could simplify this, but now we have a double borrow here without the into iterator. Fair enough. And that's collect. That's collect for us, and that's how you use it most of the time. You use it to get rid of results, which you can't get rid of, by the way. You could also say, but Sebastian, why don't you just do this?
Well, that would stop even before it comes to collect, right? That would kind of return inside of the iteration, and then not even execute.
I mean, this does not compile. Maybe we can make it compile. We can make another version of this compile, because I think it's valid, because this question mark, it's returning, or this question mark operator, it's returning from a closure. It's not seeing the outer scope, which is what the intent is, right? So this effect of returning from a method or function is not actually as composable as we want it to be, because in a way we want to say, yes, exit the parent function or method, but not the closure. Because that would be really cool. Then you really don't have to write loops anymore. Sometimes you find yourself writing out the for loop just so that you can return from your context and not from the closures context. And I think there are programming languages that have this differentiation that allow you to have special closures that are just not really closures, but, you know, kind of can exit the parent function with the same syntax, which really is syntactic sugar in a way. Like, to be able to do this, somebody has to make it work, because you are still in some function that is not your parent function. So in a way, I understand that this is not implemented that way. But yeah, this already says a lot, because we are actually able to use this from the closure, and it might have the right effect. So let's try to rewrite this for as in, now without the collect. And now we print that again. So previously we had a filter map here. And I don't know if we ever did that, but of course you can use question mark also to exit from a context that expects an option. So this filter map wants an option, and we can say unpack that string for me, and then exit early if there is nothing, and exit with none, or return, sorry, not exit, but return with none. I don't know why that is not working, because it should, I thought. Oh yeah. Right. Yeah. So that's another way of writing this. So you are very able to use question mark operator here. Mm-hmm. So as long as you have a context that that allows you to, or that wants that kind of return value that question mark wants to return. So either an option or a result. So if you are in methods or call methods a lot that have options as a return value, you can use question mark all the time, except that the error value is just a none. So there is just nothing, but early exit. And that's pretty cool to know as well, because sometimes you are in such a context, and then question mark makes great sense to use.
See. Yeah, okay, I think I understand. Because filter map wants an option, and the question mark just works with that, and then filter map knows how to deal with this. I see, okay. And the normal map didn't do this.
Yeah, normal map only returns or takes any value that you choose to return, but that's not good enough for this one. This one wants an option as a return value or a result. And that must be there. And if you have a closure that has one of these, you're good to go. Or you can maybe even emulate a closure yourself that just does the right thing. So can we do something like this? So we want a closure that returns a result of a string and UTF-8 error. And then we do this and call it. I mean, something like that should work. I mean, this is nonsense. This is ridiculous. But I think we can write that. So let s be this, and then return. Okay. S. So does that do anything? So intent here is to internally. Oh yeah, right. I should probably use this S. Yeah. Okay. That I probably, this could have worked, but I don't want to take the time to make it work because it's kind of so nonsensical. Obviously, it's ridiculous. But I try to make a closure inside of another closure that just takes something. It should take a U8 slice, and we define it so that the compiler knows that I would return a result that is either a string or UTF-8 error. So inside of this, I could now call question mark operator and repack this. And then I call that inline closure, so to say, which can obviously bind my environment here, which is also an annoying property. In this case, I probably wouldn't want that, but it can. See my little bug here that it would still use v, which probably also tells me I want to call it like this, so that this is just shadowed. So v, a lot of v, and then we call this thing, and then we say okay, because out comes a result, and I just want to bring this down to an option again. And I'm a bit surprised that this does not work in this monstrosity. Because the trait from UTF-8 is not implemented from... all right, it's the wrong type that I used here.
Oh.
I used another one. Interesting. So now this actually works. See, this monstrosity. Just to show that, yes, if the closure is the right one, we can totally do that. Obviously, this is just a very complicated way of writing this, which in turn is a very complicated way of writing what we already had. But you can. So these inline closures, I think it's also a JavaScript thing to do this sometimes, to have your own scope or another scope where you can hide things inside. I think I have written code like this for that purpose alone. But in Rust, just to say it, this is something like these inline closures. I would, if I have to write something, then I definitely want to close over something of the environment. Like I don't write a closure like this that doesn't use the environment. This one here has nothing to do. It doesn't close over anything, but I use closure syntax.
It could be its own separate function, right? There's no reason to write this as closure.
Yeah, exactly. So let's make an own function out of it, because it's pretty much the syntax already. And now we call it. How about this? Of course you can. Yes, you can define functions wherever you want to in any scope. You can have use statements anywhere, which can be useful in case you don't want to, pollute your module namespace with something that's very specific. Like sometimes you want to use some variants of some enumeration. Like let's use, I mean, these already are in the namespace, so that does nothing, but this is how you do it on your own variants. If you want to just match on, don't want to rewrite the type again. This is how you do it. But yeah, define what you want, where you want it, based on your actual needs. And that could be it. But I delete this now because it's definitely nothing I want to see again next time, because it's just too unidiomatic. That's a bit better. Okay. But that could be it. That could be all about collect into results, into sets, into vectors.
Really cool. Definitely magical, but very useful if you know how to use it.
Yes. And use it all the time, so it's very common. And I think there's a few more bits and pieces about iterators that are common that we want to know about, but that shall be done in the next episode of Learning Rust with Good Oxide. Thanks a lot for watching, everybody, and see you next time. Bye-bye.
See you soon.